Hello and welcome back to differential equations. This is part 2 of 3.1 linear second order differential equations. And we started talking about those equations with constant coefficients. The general form is that you can have any function. You see those capital A, B, C? Those are all functions. And there are other methods to use, other than what we are currently doing, to deal with those. The easiest case for us to consider and work on is going to be the constant coefficients. We also said that the second order differential equations will have two solutions, and solutions can be added together into a single solution, but it's still y1 and y2, except we put them together into one solution. It looks like it's a one solution, and we call that principle of superposition when we put them together on the pile. Then we go down to show that if you have two solutions, like for this particular equation, which is a wave equation, if you have those two, then you would say y1, y2, and then you add them together with c1, c2. We call this general solution because you have the constants c. And if you want to calculate those c's and get numbers for those, you would have to go with and call it a particular solution. You would have to do one more thing, and that is to use those two either initial conditions or initial values, whatever you want to call them, and then you would be able to calculate the values of c1 and c2 and work on this one. So now, what was the way to determine the solutions for this? We have seen that the equation, second order differential equation, can be rewritten as the second order polynomial called quadratic, and we call that characteristic equation. If you take a look at the original differential equation and the characteristic equation over here, you notice that they both have the same ABC, right? And you also notice that the R that shows up in the solution which we are guessing, e to the RT, the same R is in the equation below. So as we solve, because A, B, and C are given to us, as we solve for R, we would have two different R's. Now, the goal is to learn what to do with those different R's. And we have the two constant coefficient R's. Then we have a repeated R, and we have complex R's. We are not going to deal with complex R's now. Complex R's will be the part of, I believe, 3.3 or 3.4. I think, yeah. Probably 3.3. Yes. So in 3.3, we are going to learn how to deal with the complex R's. Today, we're only going to see what to do when we get real R's, whether they are distinct real R's or a repeated R. So now that we established this last time, I did have an example, and we scored 3 1/2. So we have a differential equation. We saw that we immediately write characteristic equation that looks identical, except with R's. We use factoring or quadratic formula or essential oils. I don't know what you gotta use to get those R's. Once you have the R's, you will immediately write the solutions. What I just circled you can actually skip, and you can immediately write the general solution. Now I want to work out one more of these examples. Hopefully I can find an example that will have also the boundary values so that we can calculate that as well. So here is another example. We can go with problem number 6 from the textbook. It says y double prime plus y prime minus 6y equal to 0. And we have y of 0 equals to 7. And y prime of 0 equals to negative 1. And we are supposed to, there we go. Good. So now, what we are going to do is solve this the same way we solved the previous one. We have r squared plus r minus 6 equal to 0. So you immediately write the characteristic equation. Now, if you want to go through all of the in-between calculations, which I did last time, you can, but you are also allowed to just jump into that line, and there you have it. Now, again, whatever method. I don't know what's your favorite method.
You just factor it out.
This one? Yeah, this one. Thank you. So r plus 3, r minus 2. So this one factors nicely. For r equals negative 3, r equals 2. Quadratic formula will work 100% of the time, right? And the factoring, only when they work out to be integers. There are other ways. You can do the completing the square and a whole bunch of other things you can do. Since now we have this, we can immediately write that our solution is equal to c1 e to the negative 3t. You can also use x. We like t better because t is time, and this is a course that gives rise to all of the physics and engineering. So in terms of time, well, you can put x plus c2 e to the 2t. And this is what would be called general solution. We are halfway there. We are able to compute C's now because the conditions are given to us to compute those C's. Now, observe that the first condition here is for the y as is. The second condition here is for the y prime. Do you have a y prime? Well, you have to get the y prime. How do you get the y prime? You obviously differentiate this. So y prime is equal to negative 3c1 e to the negative 3t plus 2c2 e to the 2t. And this is what we have. This is what we have now. So at this point, we use, and I'm actually going, because this is now new, I'll point my arrow here and I'll say use y of 0 is 7, and for this one use y prime of 0 is, I believe, negative 1. Yes. Once you plug these values in, you will have system of two equations to solve, and you will be able to compute the values for C1 and C2. And again, your method of solution, whatever you like. So here we go. The first one is So from the top, we have C1 e to the, I'll write one just in case, negative 3 times 0 plus C2 e to the 2 times 0 equals 7. And from the second one, we have negative 3C1 e to the negative 3 times 0 plus 2C2 e to the 2 times 0 equals negative 1. And then we are going to just say C1 plus C2 is 7. This is not always going to be the case. Be very careful, right? Because we have a 0, e to the 0 is 1. But if you have 1 there, then you would have e to the minus 3 floating around, right? So you have to be very careful what you are. That's why I wrote those two lines where I plugged in 0 for each t, because that's our input. And the second equation, negative 3c1 plus 2c2 equals negative 1. So with this, you have now system of two equations, two unknowns, and you can do the guess and check method. You can do the graphical approach, or you can do substitution, you can do elimination, whatever your favorite is. I'm going to multiply the top line by
3.
You want 3? Okay. We can also do negative 2. There will be smaller numbers, but whatever. Doesn't really matter. 3c1 plus 3c2 equals 21. And negative 3c1 plus 2c2 equals negative 1. Most of your mistakes on exams happen when you forget to multiply these numbers by whatever. So, well, those are the silly mistakes, right, that occur way more often than we would like as instructors. So I'm just warning you to make sure that 7 times 3 is 21, right? But usually that's where your mistakes are. If you are checking your problems on exam, right, under the pretext, let's say you care, right? You want to check. Try to find the mistake there, that you forgot to multiply one of these by the number. All right, so now the C1s drop, 5, C2 equals 20, C2 equals 5, and C1 must be 2 in order for them to add to 7. And we finally have our solution y of t. What's that function?
C1 is 3 and C2 is
Oh, well, yeah, I was just testing you because it's, yeah, I just need to make sure that you're all paying attention. Very good, very good.
Yeah, math is hard. It happens.
So 3e negative 3t plus 2e to the 2t.
You're meant to bring balance to the equation, not destroy it.
Okay, so that's gonna be the best comment.
Isn't it 4?
It's even better because of the shirt you're wearing.
Yes,
Because of the shirt.
because of the shirt.
Okay.
Yes, you heard that, right? You were supposed to bring the balance to the equation, not to destroy it. So, yeah.
4, not 2.
If you are left out of this, probably the best joke I've heard this year so far, it's your fault.
Yeah.
It's 4, right?
Particular solution.
Wait.
Oh, I'm gonna write this one down.
Wait a minute.
4?
E to the 2t, not 2e to the 2t. That's C2, right?
Yeah,
No.
C2 should be
C.
Isn't it like y equals c?
3 and 4.
There
Yes.
you go.
This
There we
is the one that we need. All right. Now this was intentional, just to make sure that
Yeah,
all of you that are writing with pens are annoyed. Good. So let's review the entire problem.
I get to slap you again.
This is going to be a question on exam 2, and huge probability on the final as well. You are guaranteed to have this verbatim on exam too, with different numbers, right? You must. On the final, it's a very high probability to get this entire problem from the first to the last row. You are solving second order differential equation with constant coefficients. In this equation, guys, we are talking about basic mechanical and electrical systems. These equations are used in your fields. So that's why this equation will be put in the word problem setting in two different sections. I believe 3.5 and 3.7 will be mechanical oscillations followed by electrical circuits. And then...
Out of curiosity, where's the y equals e to the RT come from?
Oh, that's the exponential form that we are expecting to get as the, because remember that the constant coefficient linear problem gave us a single e to the RT answer, right? Because your population model was P0 e to the KT, and all of those look the same, e to the something, right? And even when we started messing with the population in terms of the birth rates and death rates, they still had logistic model. It was still some kind of e. So the way Euler did these things, right, he says, let me try, right, and just plows through calculations. It works. There is no reason, right? So intuition, then you try it, it works out, then you work it backwards as a proof, and you seal it into the theorem, into the book forever, right? So intuition, that's where it starts, because it shouldn't be too different, right, from what the linear, because again, polynomials are polynomials, whether it's a first, second, or 100th degree. So in the next 3.2, when you see the seventh order differential equation, if you're able to factor into 7 solutions, you're expecting the same mess.
And would you apply the same method to the RT?
Well, you have to, I mean, if you can't factor, you are doomed, right? Yeah. But everything else would work the same. So we just generalize this method to higher, right? There's no reason to reiterate everything for the third and the fourth and the fifth and the sixth and the seventh, and then someone shows up, how about the eighth? All right, you do for the eighth, and then he's going to ask about the ninth, I know, right? So just because he can, right? So these are the things that we're just going to generalize. All right, so now I have to bring to a table another thing that we haven't talked about, and that is talking about independence of the solutions and calculating something is called Ronskin, which is a determinant of the matrix that will show that the two solutions are independent of each other. That will help us with the second case when we have repeated roots. Now I have to just go really quickly through the Ronskin calculation, which shows that the two solutions are independent. Please understand that dependent solution means the same solution, right? If a child is a dependent on a parent, we call that the same family, right? It's a family. It's one unit, right? Whether it's one parent, two parents, that doesn't matter. What matters is that there is a dependent, right? In the eyes of the law, claimed on taxes, okay? So if you have independent solutions, then that would be like two people that cannot be claimed by anyone. Everyone files their own taxes, right? So dependent solutions are the same solution. Independent solutions are different solutions. And you want your second order differential equation to have two independent solutions, which we mush into a same, right, using the superposition, we mush into the same expression. But you still have y1 that it's completely independent from y2. That means that they have a different shape of the curve. Now, if you take a look at the two solutions that we just had, one solution was e to the negative 3t, and that one is a decay, e to the negative 3t, and the other solution is e to the 2t, which is the growth, right? They're clearly two different solutions. right? So these two solutions are different, even though they belong to the same, right, exponential function. They are different solutions because the curves are different. Now, even if you have two curves that are, let's say, e to the t and e to the 2t, they are going to rise on different rates, and they are still different functions. They are different solutions. So you have to be careful what it means to be independent and what it means to be dependent. Dependent ones are the ones that are multiplied by a constant. They don't change the shape. They just change either how fast they rise, or they change, or you can add or subtract a number or shift left and right, right? Those would be dependent ones. So you can have this situation, which is okay, and you can have this situation where you have, let's say, like this, e to the t, and then you have like this, e to the 2t, let's say. So you see that one curves more and goes up faster, right? These are your t axis, or x axis. Right. So that's it. Now, to check for independence of solutions, we are going to use what is called Ronskin. That's the last name of the person who developed the procedure to check the independent solutions. And let's write that. So linear independence of two functions and we say any two functions that are not constant multiples of each other. That's all we have, right? So any two functions given, definitely x and e to the x. I mean, they are not belong to the same family of functions at all. E to the x and sine x, e to the x and ln and x, and any polynomial with any transcendental mixed in. If they don't belong to the same family of functions, they're clearly independent. But then when you go within the family, I just explained that e to the x, e to the t and e to the 2t are also independent, right? Now, follow up to this, to check, use what we called Ronskin. Now, Ronskin is defined, Ronskin of y1 and y2 is defined as the matrix of the function determinant. That's why I have, okay, those of you who did not take linear algebra, I'll have to explain the notation. But right now we're writing y1, y2, y1 prime, y2 prime. This is, and the way this is computed, please look at the board. I am erasing this. The way you compute it is that. I will draw this one more time. You will see I am starting up here, and then I'm going to do this. So the way I'm computing this is y1 times y2 prime minus y1 prime times y2. Do we all see the symbol over here? As I draw this symbol, I start at y1, I go to y2 prime, then I say minus, and then I go this way and exit there. Now, it's not just how you compute, but how you interpret this. If the solution is 0, then solutions are linearly dependent. If it's a non-zero solution, they are independent. So, we can have two cases equal to 0, dependent, not equal to 0, and dependent. And that's the one we want. Independent solutions. Remember, we need 2 solutions for the second order, and later we'll need 7 solutions for the 7th order in the next lecture. Cool. So example now is what's happening with our y equals, what do we have with all those numbers? We don't actually need those c's at all, but really. Three and 4, okay. 3e negative 3t plus 4e 2t. To calculate Ronskin, we do not need to worry about 3 and 4 at all. We can just say e to negative 3t, e to the 2t. We do not have to worry about the solutions there. And then we are going to just compute the Ronskin by working out the determinant of e to the negative 3t, and then e to the 2t, and then the derivatives, negative 3e to the negative 3t, and 2e to 2t. So you will always have your first row, because that's given to you in a solution, and then you have to compute the second row, because those are the derivatives. Now, we are going to follow the pattern. So we're going to say e to the negative 3t times 2e to the 2t minus negative 3e to the negative 3t times e to the 2t. So you follow it down the way it's the symbol. And we have 2e. And now what happens with exponents when we multiply the e's?
Negative t.
They add. Very good. So that's negative t. And then we have plus. This becomes 3e to the negative t. And we have 5e to the negative t. That's different than 0, which says it's linearly independent. Yeah. Actually, I'm going to go with the next row over here so it's not mushed in there. So solutions are linearly independent. There we go. I'll put a big green check mark. Now, we had this talk. I hope you understood what the independence is all about. I hope you understand how to check independence. And now the next order of business is going back to our constant coefficients, and we are going to have a case where you have what we call a repeated root. Repeated root meaning R1 and R2 are the same number, which clearly would give you the same solution for both R's, right? So, repeated roots, R1 equal R2 equals just R. This is actually case 2. Our first case was when there were two different r's. We just had the example, one was -3, the other one was 2. That was the case 1. Case 2 is repeated roots, and it will have a different solution because obviously it's not going to pass Ronskin, right? It's the same solution, same function. It's not going to pass Ronskin, so we can't use those two solutions as two independent solutions. So what I'm going to do now is I'm going to say that for the differential equation a I double prime plus by prime plus cy equals 0, we are going to have a solution that goes, well, sorry, first characteristic equation ar squared plus br plus c equals 0, from where we are going to get r1 equal r2 equals r, because we are in that case. For some a, b, and c, this is going to be the case. We are now, maybe I should write over here, this is case 2. And let me go up, come on, and write case 1. Just want to see, where do I write case 1? Where is the best? Oh, here. I actually didn't define it, but here. R1 different than R2, real, case 1. This is why I said you should have on your notebook, on that hardcover, you should start listing these things, because we interrupt these methods with other things to explain what we need in between, and then you might lose the sense. And also, we're going to cover the third case in 3.3, right? So they're not taught together, case 1, 2, 3, right? Most of the time you learn something, you learn case 1, 2, 3, right one after the other, right? Well, in this case, you didn't. So please have some kind of a place where you're dumping all of these things one after the other. So you say, okay, if I have a constant coefficient, second order, and I solve characteristic equation, these are the 3 outcomes that I can have, right? So the first outcome is different values real. Second outcome is this one. And for the second outcome, because they are linearly dependent, you will multiply the second one, or you can do the first one as well. You will multiply the second one by an independent variable. So the solution over here will be y of t is equal to c1 e to the rt plus c2 e to the rt. So this t is new. Yeah.
Oh boy.
I know. So that's not the one.
There you go.
So this is what we have. And because this is what we have, we are going to now there we go. And because this is what we have, we are going to now have an example of y double prime plus 10y prime plus 25y equal to 0. So the solution for this should look exactly the same as the previous one. You will calculate your r, and then you should write this one. I'll be right back. Give me 1 second. Complete this example. I'll be back in 1 minute or 2.
Okay, so how much did I miss?
I mean, it didn't take, I don't think the greatest notes. You know that.
Yeah.
So we did this example using this stuff. Yeah.
I'll just watch the video.
That's a better idea. That's a lot better of an idea.
Yeah.
The only problem is you didn't give us any to set it to.
Oh yeah.
So we only have the
I mean,
negative
is
5.
it in the book?
Well, yeah, we only have negative 5t and negative 5t. Wait. Oh. No.
No.
Nope.
If I figure it out, I'll tell you.
I'm looking for it. Oh, y prime. No, that's just 25. No regular.
So what is your R? What is your R?
So the problem in the book is negative because we don't have anything set to y for y0 and y prime 0.
Oh, we don't care about C's.
Oh, so
I was just...
Oh, it's going to be negative 5 or positive. R is going to be negative 5, but it's
Yes.
positive.
So R should come out to be a negative 5, and you should just write this type of a solution. I did not give you any of the coefficients, right? Initial points to calculate coefficients C1 and C2. So you, at best, you can get the general solution for this one. So we are going to... You can factor this, or you can use quadratic formula, whatever, right? Pick your point. You can do also completeness square. That's another thing. We write immediately r squared plus 10r plus 25 equals to 0. And we are doing the r, right? And now we are going to factor this as r plus 5. Another r plus 5 equal to 0. If you are not seeing the r plus 5 squared, then, right?
Is that kind of like how it works with partial fraction?
That's yes.
With an irreducible.
So you see that all of that is correct.
So when it goes to third order, it's going to be a similar situation with 3,
Mm-hmm.
where you just x and then x squared. Okay. Or t squared.
So now we can see that the solutions are repeated. So R1 is equal to 5, which is equal to R2, which is also equal to 5, and we're just going to call it R equals to 5. And we immediately feed that into y of t is equal to...
Wait, wouldn't it be negative 5?
Yes, negative 5. You are right. Negative 5, and negative 5. So e to the negative 5t plus c2t e negative 5t. And that's it. So this is what we have as our, what we call general solution in this case. General solution, we do not have the points to compute anything else. And this is where 3.1 ends, right? We're going to take a short break. When we come back, it's 3.2, which is the higher order, 3rd, 4th, 7th, 107th, right? So generalizing this to any order. And then it's the next class, right, on Wednesday, when we see the third case with the complex solutions.
I was going to say, problem 10 is exactly the same, just minus 10y prime.
Oh, okay. So we got hit. We hit this close to home, huh? I wanted to see something else if we could. Oh. There's one more thing worth mentioning before we, just in case, let's just mention one thing. This is going to be related to the case 1. Let's go blue over here. So related to case 1. And that is, if you get exponents, so this is just related, it's a side note technically. It's one of those things where you can just claim you can flex in mathematics, right? When you have a case where your R1 and R2 are what we call additive inverses. That means they're adding to 0. So you have a -3 and a +3, or -5 and +5. So only when they are additive inverses like that, you can rewrite your solution as cosine hyperbolic or a sine hyperbolic, depending on coefficients. Remember that e to the x plus or minus, depending sine hyperbolic, cosine hyperbolic. So e to the x plus e to the, yeah, and then you just time 2 times, yes, because divided 2.
Yeah. Okay.
So that's just in that case. So related? It's not, for whatever reason, it's not cooperating for me to write now. But if R1 equals, let's say, A, and R2 equals to -A, then your solution Y1 is e to the AT, and a solution Y2 is e to the -AT. And we know that the linear combination of these can be represented as y equals EAT plus E negative AT. And then that can be represented as, in this case, cosine hyperbolic, because we need over 2, we'll just say 2 cosine hyperbolic AT. It's just a side note. Again, there are ways in which you can, manipulate this and so on, so that's that. So some of the solutions can be represented as hyperbolic functions. Generally, electrical engineering is enjoying these kind of things. Bye.